In the previous video, we solved the phi equation for the hydrogen atom, and to do that, we had to separate the theta and phi equations. So in this video, I'm going to solve the theta equation, which is what we have right here. Now, in case you haven't watched the previous videos, I'm using a slight different notation from the book because K is what is usually called just L times L plus 1. But as I have said before, I really don't like to just go ahead and plug in whatever the books tells us, because many times they don't explain the reason for these, for naming it like this. And I think that especially in this case, it's really not intuitive. And I've read a few times that they just say, like, yeah, we will call it this way for reasons that will become apparent later, and they never mention it again. So I think it's just good to make sure to show where it comes from. Okay. So this is our equation. How do we solve it? Well, first of all, we have this theta function down here. We can just multiply through so that it is a little bit simpler. Let's see. So we're going to get big theta here, and we can now just write this to the left side, basically by subtracting it, and we can then factor out this theta. So we get k sine squared minus m squared times theta. And this has to be equal to 0 then. And I will also get rid of this because I already discussed it. And well, I'll just put this here. Okay, so this is the equation that we want to solve. Now, how to solve this? This is, well, not easy at all. So I don't blame you if you don't really see how to proceed. Something that you could try here is, well, there's a lot of sines and a lot of derivative of sine, and there's another sine squared. So, you know, sine squared is 1 minus cosine squared. So I guess it kind of makes sense to say, just try and see what happens. That is one way to see it, and say, okay, since there's a lot of sines and derivatives of it, we could take some variable to be cosine, because when we take its derivative, it's going to be sine. And then we're going to get cosine squared, because sine squared is 1 minus cosine squared, and since our variable is cosine, we can then write it as that. So if that didn't make much sense, don't worry. Another way to see it is to see that this might be kind of similar to a very well-known mathematical function equation, which is the Legendre equation. In this case, it's going to be closer to the associated Legendre equation. But since you probably don't have much experience with that, I'm not going to mention it until we actually get to it. So for now, let's just say x is equal to cosine theta. Now, this is a trick, to be honest. So if you wouldn't have thought of that, don't worry. I wouldn't have either the first time I saw this. It's just a bit hard to, this is a hard equation, so don't worry about it. So the differential here would be minus sine theta d theta. So let's now take a look at it. So we now want to write all of this in terms of our new variable, and please don't confuse this x with just the coordinate x and xyz. This is just some random variable x, and just to solve this easier. So what can we do here? Well, let's see. What is this d by d theta? So let's say d by d theta. Well, if we apply the chain rule here, we can write this as d by dx times dx d theta. And that would be quite nice, because that way we're going to go from this d by d theta to d by dx, which is much better to it. Actually, there's no need for the partials anymore. So, well, I'm going to leave it like this, just so I don't use much time erasing it. But for now, I'm just going to go for total derivatives, because I had this notation from when we still had the phi. Well, anyways, so what is dx d theta? We can get it from here. Dx d theta is going to be minus sine of theta. So d by d theta will actually just be minus sine theta, whoops, normal, total derivative dx. So let us now write that into this equation. So we get sine theta times minus sine theta d by dx, and this is going to be acting on, actually, yeah, then let me change the way I'm writing this. let's see, yeah, sorry, this is just this d by d theta here. So this is going to be acting on sine theta, and now we have another d by d theta, which will be minus sine theta d by dx, which is going to be acting on this theta function. And I think that's the correct amount of parentheses. And then we have plus k sine squared theta minus m squared acting on this theta function. Okay, I'll grab this and take it to the next slide. I'm kind of covering up the 0, but I think it's okay. Now let's just multiply through here. So we get minus sine squared theta d by dx of minus sine squared theta d big theta dx, and then we have plus k sine squared, there's no difference here, nothing changed, theta equals 0. Okay, now we can just take this minus sign that is in here and put it in front so that they cancel out. And what can we do next? Well, we know that our x is cosine of theta, but sine squared we know is 1 minus cosine squared of theta, which means that now we're going to get 1 minus x squared. And that way we now will have gotten rid of all of the thetas, at least the variable, and we only have this x. And that's going to be a lot easier because, well, polynomials are easier to work with many times than these trigonometric functions. And that was the point of this change of variables, choosing x equals cosine x. So in order to know that we have to do that, you have to know that when you apply the chain rule, you would have gotten another sign, which will give you sine squared. And with sine squared, you can write it as 1 minus cosine squared, which is just 1 minus x squared. That is how you know that you have to use this trick. But as I said, if you have never done this before, it's not really something you're going to think about. I mean, I would never have thought of this, and that's why, well, it takes teams of scientists usually, but it's fine. Let's just go for this. So sine squared is 1 minus x squared, sine squared here as well, 1 minus x squared, and here k sine squared is also going to be 1 minus x squared. So, well, let's see. Now, everything depends on x. Let's just take this derivative here. So we got 1 minus x squared. Let us go ahead and take this derivative. So what do we get? We get, well, the derivative of this is just going to be minus 2x, and because it's product rule, we just keep the big theta dx, and now plus 1 minus x squared times the derivative of this. So we're just applying the product rule here, dx squared. And, well, everything here is going to be the same. Oh, whoops. 1 second, let me fix this. Okay, I think I went a bit too far. Okay. This plus this. Nice. So what can we do now? Well, the simplest thing would be to divide by 1 minus x squared, so that we get the following. Well, I'm going to write it as minus m squared 1 minus x squared. Okay, so this is what we get now. So this is quite close to a very well-known equation. I'm going to just write it slightly differently so that it looks even more like that equation. So I'm going to do it like this. So 1 minus x squared d squared theta dx squared minus 2x times first derivative plus this right here. So there's a very well-known equation, and honestly, to solve this, it is kind of important to know of its existence, because that way we know what we have to get to, because if we want to transform this into what is known as the Legendre equation, Legendre Differential Equation, which is 1 minus x squared d squared of, well, some function, right, dx squared minus 2x, I'm just going to write it as f prime, plus, oh, there's double plus here, whoops, plus, it's n plus 1 f equals 0. So that's what we want to get to here. At least that's the shape that we want to get to. What we have right here, this is just called the associated Legendre differential equation, and we want to see how it is that we can solve it. And for that, we want to get to the what is something of this form, out of the Legendre equation. So how can we do it? Well, let me first, I'm not sure if I should erase this. Yeah, I think I just erase it for now, because you can just go back and see it once again if you want to. Okay, so we want to get to it, and we can actually see that we are going to be quite close to that case if we have m equals 0. So here's actually where we can see that k, in order for this to be what we want, k should be of the form L times L plus 1, where L is an integer. And that's actually where this L times L plus 1 comes from. So that's going to be the first thing that we change here. So instead of k, we're going to have L times L plus 1. But we still have this extra term here. So we're going to have to use a substitution to manipulate it and try to get it to be what we actually want it to be. So in order to do that comes something that is probably not going to be very intuitive. There's a few ways to solve it, but I think that this is probably the easiest one. I really try to look at into as many solutions as possible to try to find the easiest one. But what we have to go for is the following. We have to say, okay, our theta function, our solution, let's look for solutions of the form 1 minus x squared to the m halves power times some function that we're just going to call p that depends on x. Okay, and now this might seem a little bit arbitrary, and you're going to see what comes. So the whole idea of having it to the m power is going to be because we have these m's lying around and we want to be able to relate them, and this divided by 2 will cancel out this squared factor that will turn into a 2 when we apply the chain rule. So, but you will understand better as we move forward. However, it's still a trick and it is going to be hard the first time. Let's do that then. So when we take the first derivative, we're going to get this theta prime will be, well, now there's a product rule and here we have to apply the chain rule. So we're going to get m halves times the chain rule from here. So we get minus 2x times 1 minus x squared to the m half minus 1 power times p. And now the second part of the product rule, we get 1 minus x squared m halves p prime. Here we can simplify a little bit. This 2 will cancel out the 2 in the denominator. So we are just going to get minus mx. It's going to be minus mx. And now both of these, though, are multiplied by this 1 minus x squared m half. So let's just factor that out. So this is a little bit simpler. So we get 1 minus x squared to the minus m to the m half power, sorry. And this is going to be a product of, let me write this first because it's positive and I like it to be that way, p prime minus mx 1 minus x squared, and this is going to be to the, whoops, to the minus first power. So this is going to be the most compact form for this that we're going to use later. However, we still have to derive this, and well, it doesn't really matter which one you choose. I like to derive this, but this one is easier to use later on, or you can just derive this, use the derivative on that, it doesn't matter. I'm just going to use this because now we want to determine the second derivative. I'm going to write it here so that I can see it. So the second derivative, I will use a different color so that it is a little bit less messy. So the second derivative will now be, well, here we have to apply product rule several times. So first we derive this, which is just going to be minus m times 1 minus, well, basically times everything else, m half minus 1 p. And now we leave the first part b, just minus mx. And now we derive the second part. So that's going to be, well, whatever order we want to do first. We take the exponent down, and that's going to be m half minus 1. And now because of the chain rule, we get minus 2x. And now finally 1 minus x squared m half minus 2 times p. And now we leave the first two terms b, and we apply the derivative to the p function. So it's going to be minus m half minus 1 p prime. And now for this, we are going to get plus m halves minus 2x times 1 minus x squared m half minus 1 p prime. And now we leave the first part b, and we just apply the derivative to p minus x squared m half p prime prime. Okay, so that is the second derivative here. Now let me change color once again, because I want to now just write this but simpler. How can we simplify this expression? Well, first of all, notice that all of these terms have 1 minus x squared to the m half power. So let's factor that out. So we get 1 minus x squared m halves, and this is going to be a product of all of these things. So let's begin with the second derivative. Here we just get p prime prime. Okay, so I already considered this. I'm just going to put a line there so I make sure that I don't consider it twice. Here we can actually simplify a few things as well. So we got this 2 and divided by 2, so we can just write it as minus mx. So minus mx. So let's now go for everything that is multiplying p prime. So here we have minus mx times 1 minus x squared to the minus first power. So we already used this. And here we have actually the same thing, minus mx, 1 minus x squared to the minus first power. So let's just write a 2 in here. So 2. Okay, so that's everything that has this p prime. Let's now go finally for everything that only multiplies p. So we are going to have this right here, which will be then minus m 1 minus x squared to the minus first power. And then we have this right here. So here we can simplify a few things as well. So this 2 that is multiplying, we can actually apply it on this parenthesis, so it cancels out the m that is dividing, and this minus 1 will be minus 2. The other thing that we can do is you combine this minus and this minus, so we get a plus, and this x can actually just be written in here with the other one, so we get x squared. Okay, so this second term then will be plus mx squared m minus 2 factor of 1 minus x squared to the minus second power. And we can actually just multiply through by this parenthesis now. And that will leave us with the following. So from the first multiplication, we get m squared x squared, and from the second one, we get minus 2m x squared. So let me now replace this by that. So from the first one, we said m squared x squared, and that is multiplied by this. So 1 minus x squared, and then we have minus 2m x squared times this thing. So this is our theta prime prime. And what do we do with this? What is the whole point of this? Well, let's go back. Remember, we want to be able to write it into this equation. So basically replace this by the second derivative, replace this by the first derivative, and replace this by this ansatz. And we hope that when we do that, we're going to get an equation that is easier for us to solve. So, well, let's now go to a new page. So just to make sure that it's clear, and what does that mean? That means that what we have for the second derivative, we have to multiply by 1 minus x squared. What we have for the first derivative, we have to multiply by minus 2x. And then we have to add this to this ansatz times this thing over here. And just because this expression is really, really long and I don't have that much room on my screen, first I'm going to add the second derivative to this first derivative, and then the result of that I'm going to add to this right here, okay? So let's write that down. Now this is our second derivative. I'm going to go back to red now, and what we want to do is multiply this by 1 minus x squared so that we can then add it to the rest, because that's what's in our actual equation. So when we do that, well, this thing right here will be the same, 1 minus x squared m halves factor of, and now when we multiply by 1 minus x squared, we get 1 minus x squared p prime prime. And then we have plus p prime factor of minus 2mx, and this here cancels out. So basically this is just going to be minus 2mx p prime. Okay, so it's already looking better. Now this part right here, we get plus p factor of minus m, which is because this cancels out. Oh, this was supposed to be to the minus second power, by the way. I left it out. Sorry about that. Okay, so when we do that, we get plus m squared x squared times 1 minus x squared to the minus first power minus 2m x squared 1 minus x squared to the minus first power. So this is now what we have for our second derivative. So let's replace this in blue by this, because we are interested in what is in red, because that's what we can put into our equation. Okay, now let's do the same, but for the first derivative, which is going to be this. So we have to multiply this by minus 2x, because that's what is in our equation. Okay, so now let's just take minus 2x times theta prime, but I don't want to use red actually. Let's go back to, now let's stick to white because it's the same color that we have here. Okay, so let's multiply this by minus 2x. So we are going to get 2mx squared times, let's also factor out this. So we get 1 minus x squared m halves factor of 2mx squared 1 minus x squared to the minus first power minus 2x p prime. So this is what we get from this first derivative part. Whoops. And okay, I need to use a smaller eraser apparently. And now what we want to do is plug this into the first half of the equation, because as I said, it's going to take a lot of space and I want to try to keep this as understandable as possible. That's why I'm going to do it by parts. So first I add these two things and then I add the third part. So when I do that, what do we have? Well, everything is multiplied by 1 minus x squared m halves. So that's just going to be 1 minus x squared m halves factor of, well, first we have this prime prime here, and there is nothing else that involves a second derivative. So that's just going to be by itself minus x squared p prime prime. Now, what involves just first derivative, it's going to be this here and this here. Well, wait a minute, here I'm missing some p here. Let me see what this was. I think that was regular p, but I want to make sure. Yes, there's supposed to be a p in here. I'm sorry about that, I left it out. P. Okay, so with p prime, what am I going to get? I put these two together, it's going to be plus p prime factor of minus 2mx minus 2x. And well, what can we do here? We can factor minus 2x, so we get minus 2x m plus 1. So I'm going to get rid of this and write it as, oh, I need to get rid of the plus 2, minus 2x m plus 1 times p prime. Okay, so it's already looking a bit more compact. And well, we still have all the p terms. So let's see, that's going to be plus p factor of, let's see, we have minus m plus m squared x squared 1 minus x squared minus 1 minus 2m x squared 1 minus x squared minus 1. And in this part we have plus 2m x squared 1 minus x squared to the minus first power. And so actually this and this will now cancel out, so this will also be a little bit simpler. So this just goes away, and I think I can even fit this into this right here. No, it's rather not do it, it's too close. Okay, so this is what we get when we add these two parts together. And remember, this is not the entire equation. We still need to add one more part to this. We need to add, let's go back to the equation, we still need this. So we have to add L plus 1 minus m squared 1 minus x squared to the minus first power times, now what, let me close this parenthesis by the way, the one that we start here, times 1 minus x squared m half times p. Okay, so this is the entire thing. So let's now include this into this factor here. So I'm going to get rid of this because now it's going to be included in the one that is multiplying all of this. What else can we do? Well, now let's take a moment to just look at the terms that are with this p. Okay, only the ones that are being multiplied by p. So what do we have? We have, well, just factors of p, so I'm not going to write p itself. I'm just looking at what is inside of these parentheses, excluding this L plus 1 because there's nothing I can do there. That's just going to be the same. I'm just looking at these three things. What we have then is just going to be minus m coming from here plus m squared x squared minus m squared, and all of this divided by 1 minus x squared. I just put these two together and wrote this as it is dividing. And now let's take common denominator here. So we get minus m times 1 minus x squared. So that's just going to be minus m plus m x squared. And then we put this together with everything else. So plus m squared x squared minus m squared. And all of this divided by 1 minus x squared. So let's now factor out an m here. So we get minus, m factor of minus 1 plus x squared plus mx squared minus m, and well, all of this is going to be divided by 1 minus x squared. Now what can we do here? Well, let's begin by factoring out an x squared inside of this. So we get m divided by 1 minus x squared factor of, then we have x squared factor of m plus 1, and then what do we have? We have minus m plus 1. So what we can do here actually is just factor out now m plus 1. And when we do that, we get m plus 1. And because m plus 1 is multiplying x squared, and it is multiplying minus 1. And this is being divided by 1 minus x squared. So if we now just take a minus out of this, so we write minus this, we can flip the sign of this. We are not doing anything illegal here, we're just flipping the sign and putting a minus outside to compensate. We get minus x squared up here. So now this 1 minus x squared will cancel each other out. So all that we are left with is minus m times m plus 1. So that means that in this expression, all of these things right here, all of these things will simplify to just L plus 1 minus m plus 1. So this is going to be the equation that we are left with and the one that we now want to solve. And by the way, this is equal to 0. okay, because we already added everything together and it has to be equal to 0. Just as a quick reminder, that's why, right? There's this 0 right here. Okay, so new slide. This is the equation that we now have, and this is now the associated Legendre equation in its most common form, and we now want to solve this. And the question is, well, how do we solve it? Well, let's just take a look at this. The thing is, I'm just going to remind you quickly of the Legendre equation. Now, this is a little bit annoying because it's really hard to solve this if you don't know the Legendre equation. So how could you solve it if you've never seen it? Well, you have to kind of look into some of the most known differential equations and see that this kind of resembles it, because the Legendre equation is just 1 minus x squared p prime prime minus 2x p prime, and some function, not necessarily called p, plus l. Well, before we called it with an n plus 1, but it's the same idea as l, it's just some constant, p equals 0. So if you take a look at these two equations, this one right here is actually the same as the Legendre equation. If m is 0, because if m is 0, then, well, this is 0 and this will be the same as this. Here m is 0, so this will be the same as this, and well, this is already the same. And why is it interesting, by the way, why we're not considering this part? Well, because since it's a product, either this has to be 0 to satisfy the equation, or this part has to be 0 to satisfy the equation. And although this part is valid, it is mathematically valid, we can find a solution, that solution will actually will not be physically acceptable. And now it is, although not too interesting to look at it, and it will be quite a lot of extra effort. That's why I'm just going to leave it there, and we're going to look for the solution of this equation right here. That means we want to solve 1 minus x squared p prime prime minus 2x m plus 1 p prime plus p factor of l plus 1 minus m plus 1 equals 0. This is the equation that we want to solve. And as I said, if m is 0, this is just going to be the Legendre differential equation. So what happens when m is not 0? Well, that is something that we're going to take a look at in just a minute. First, let us solve this when m is 0. So when m is 0, as I said, this equation will be the Legendre differential equation. This right here. So let us solve this equation. Okay, so how do we solve the Legendre differential equation? Well, let us just go ahead and use the Frobenius method. Just let us use solve it by power series. So let's say, okay, we want to look at solutions of the form, so infinite sum from j equals 0 to infinity of some constant a sub j times x to the jth power. That means that its first derivative is just going to be, so p prime is going to be from the sum from j equals 0 to infinity of a sub j times j x to the j minus 1 power. And the second derivative then will be p prime prime. This will be sum from j equals 0 to infinity a sub j minus 1 x to the j minus 2 power. I'm covering it up a little bit, but it's just j minus 2 there. Okay, so let's plug all of this into the differential equation. So we get 1 minus x squared p prime prime, which is just going to be sum j equals 0 to infinity of a sub j times j minus 1 x to the j minus 2 power minus 2x sum of j equals 0 to infinity aj x to the j minus first power plus, and by the way, instead of writing n plus 1, let's just use it at l plus 1, because that is the constant that we are using in our particular problem. And instead of p, sum of j equals 0 to infinity of aj xj equals 0. Okay, what comes next? Now we are going to want to multiply through in all of these parts. So first, this 1 minus x squared. So when we multiply by 1, we are going to get this. The same, whoops, I think I control X instead of control C. Okay. And then we have minus x squared times this. That means we're going to get sum from j equals 0 to infinity of aj, j minus 1, x to the jth power, because we multiplied by x squared, so the power went up by 2. And here we have minus 2 sum of j equals 0 to infinity aj, x to the jth power, plus, and this remains the same, l plus 1 sum of j equals 0 to infinity a sub j, x to the jth power equals 0. Okay, so we're making progress. Now remember, how do we solve equations by this method? Well, what we want to do is just put all of our x's to the same power, so that we can put everything inside of one sum and say, okay, just the argument here has to be equal to 0, and then we see what the condition on the coefficient is for that to be true. So let me take this to the next slide. I'm going to have to put it a little bit there so that it isn't covered up by my camera. Okay, so how can we, because we have xj, 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 but here it is xj minus 2. So to solve this, we want all of our x to the jth power, all of these things to have x to the jth power. And right now, this one right here is causing problems. So how can we solve it? Well, we can see that right now, if j is equal to 0 is plugged in, this is going to be 0. And if j is equal to 1 is plugged in, it's also going to be 0. So this is actually starting from 2. And now what we can do is shift the index, which is a regular property that we can use in the summations. That means we are going to go from j to j plus 2. And in order to do that, our sum now is going to start in 2 places earlier. So that means it's going to start at 0, but to compensate, all of these things will now be j plus 2. So it will be a j plus 2, factor of j plus 2, j plus 1, x to the jth power. And now if you see, this is the same thing as we had before, right? This is going to begin at 0, being this first part, which is just j equals 0, is the same as before using j equals 2. It's still just the same term. We have not changed anything in that sum. So now let us factor all of this. So put everything inside of the same summation. So we get this factor of x to the jth power. And then we have, well, in this first one, we got a j plus 2, j plus 2, j plus 1, minus what comes here, which is just minus a sub j. And actually there are several things with a sub j, so I'm just going to factor all of it. So just put a plus sign here. A j, this is minus j, j minus 1, minus 2j, and here we have then plus l plus 1. And all of this has to be equal to 0. So in order for that to be true, we need that this thing right here, the argument, needs to be 0. So that means, let's see, this has to be equal to 0. And from that, we can now just determine a j plus 2, which is our goal in these power series method. So now we just put this to the left-hand side, so we're going to get, this will be positive, so we get 2j plus j times j minus 1 minus l plus 1 divided by j plus 2, j plus 1, and this will be multiplied by a sub j. Now we can still manipulate this algebraically a little bit by just multiplying through both of these parentheses. So we get 2j plus j squared minus j minus l squared minus l. So here, and this is going to be divided by the same thing, j plus 1. So here right away we can see we had 2j and minus j. So let's just go ahead and get rid of this j and of this 2. They just cancel out. Okay, so let's go to next slide. Oh, I think I didn't write the aj, sorry. aj plus 2 is equal to this times a sub j. Oh, that was not where I was. I just want to add this to make sure that it's clear that that aj is supposed to be there. So what can we do here? Well, we can see that we got j squared minus l squared, but that is just j plus l, j minus l. Because when we do that, now we're going to get plus j minus l. And well, divided by the same thing. And why is this interesting? Because now we can factor by j minus l. Because we got j minus l that is multiplying both j plus l, but also it's multiplying 1. So we get j minus l factor of j plus l plus 1. And this is a way that is much more intuitive to see the pattern and what's going to happen with these terms. Oh, and aj. So this also, by the way, we have aj plus 2. That means that our terms will be either even or odd. Because remember, our solution, right, which is p, this is just going to be of the form of some summation, j equals 0 to infinity, of aj xj. And if we have any of these, for example, a1, then we are going to go to a3, a5, a7, and something, and like that. We are only going to be in the even or odd powers. And similarly, if you start with even, you're just going to go a2, a4, a6, and so on and so forth. You can't really go from even to odd. And also notice that this depends on L, right? There is this L here, and it depends on that. So that's also quite interesting. Our solution, which is P, will depend on the value of L. So just let's take a few examples. We know that L has to be an integer. That's kind of a condition of the solutions of this. So I haven't really explained that too much, and that comes more from this mathematical part of the solution that I don't want to name just yet because we haven't quite gotten there. But let's see. So let's say that we're going to go for L equals 3, for example. So let's see what happens in this. We will have that a j plus 2 will be j minus 3. J plus 3 plus 1, so basically j plus 4, divided by j plus 2, j plus 1. Okay, so what values of j can our solution have? Because remember, our solution is just the value of all of the j's. So, well, let's see what happens if we begin at 0. So let's see, if j is 0, we get that a2 is going to be 0 minus 3, then 0 plus 4, and then 2 times 1 times a0. And what happens then with a4? a4 will then be, that means j equals 2, that's going to be minus 1 times 6 divided by 4 times 3. And a6 is going to be, well, this time j is going to be equal to 4, because remember, we're going only in even, we can't really go from one to the other. That's going to mean 1 times 5 divided by 6 times 5, and so on and so forth. And the thing is, what's happening here is that this is always going to keep increasing. And we want to have some sort of a finite solution because it still has to be integrable. And as j goes to infinity, these coefficients are also go to infinity. So if we have L equals 3, and actually this is going to be true for any odd value of L, then the even series will not terminate. It will just go off to infinity. And that is a problem. Because that means that if we take L equals 3, then we just cannot consider the even solutions. We can only go for odd. So let's now try that. So let's go for odd solutions. So our first solution, if L is equal to 3, is just going to be, well, a1 is just a constant of integration in these problems. It's just a1. So the only one that's interesting is going to be a3. So a3 will be, well, j minus 3. So that j is 1 right now. So j is 1. That means we have 1 minus 3, which is just minus 2. So minus 2 times j, which is 1, so times 5 divided by 3 times 2 times a1. So this is just going to be, let's see, minus 5 divided by 3 a1. And what is a5 going to be? A5 is now going to be, and take a look at this, j is now 3, so now we have 3 minus 3, so this is just going to be 0. So our power series terminates. That's very important. And what would be the result here? Remember, this is very important. Our solutions, which depend on the value of L, and in this case, L is going to be 3. So in this case, this third polynomial, because these are polynomials, is going to be a1 times x minus 5/3 a1 times x cubed. And this is a solution for the problem. You can just plug this into the equation and you will see that this indeed satisfies it. And you can see there's an infinite amount of solutions, there's an infinite amount of polynomials, and this is the formula with which you can determine each of them given a certain L. You could have done the same procedure for example, L equals 4 or something, and you would have gotten your polynomial. And these polynomials, which are P sub L, are called the Legendre polynomials because they are the solution to the Legendre differential equation. And this is then our solution to PL, because this is what's going to give us the solution to the Legendre polynomial differential equation. However, that was not the only thing that we're looking for. And by the way, there is an easier way to determine them. I think it's called the Rodriguez formula, which gives you, you say, okay, I want the polynomial for L equals 5, and it's just a formula that involves the derivative of some function, and it just gives you the answer right away. However, to derive this is more of a mathematical thing, and there's a ton of properties of these polynomials. There's orthogonality relations and a lot of things. But if you're interested in that, you can just check the Legendre polynomials, or if there's a lot of interest, I can make a video on them. But for now, this is fine. We can determine all of them using this recursion relationship. Okay, so why did we do this? Let's go back just a little bit and see what the point of this was. Let me see, where did I have my equation again? Sorry, I'm a little bit lost here. Okay, so here we are already solving it. Well, I'm not sure where I left this. Just 1 second. Okay, here we are. So remember, what we were doing is we were solving for this. So we determined this P that we now know depends on L. And the whole idea of this was to solve this thing right here. And we used this transformation and all, and we eventually got to this equation. Remember, and we said, okay, so what can we do now? Let's just go for the case where m equals 0, and what we are going to get is going to be the Legendre differential equation, which is actually written right here. Right? We took the case where m equals 0, and we got the Legendre differential equation. So what happens now if m is not equal to 0? Because we know that if m is 0, then our solution to this equation is just going to be the Elf Legendre polynomial. Right? That's what we just determined. But what happens if L is not equal to 0? Because we know L can be an integer, just general integer. Okay, let me get rid of this. Okay. So there's, once again, several ways to prove this. I really try to find the easiest one. And the best trick here is to take a look at what we have and to say, okay, let's take the derivative. Why? Once again, this is a trick, but it is much simpler than the alternative. So let's just take the derivative of this and see what happens. So let's see. We get 1 minus, well, let's take the derivative first of this. So we get minus 2x times p prime prime. And now because of the chain rule, we get 1 minus, product rule, sorry, 1 minus x squared p prime prime prime. So third derivative of this, minus, and now we take the derivative of this. So we get minus 2 m plus 1 p prime, and now we get minus 2x m plus 1 p prime prime, and finally we have to take the derivative of this, but because this is a constant, it's just going to be p prime l plus 1 minus m plus 1. And this has to be equal to 0. So here we took the derivative. Let's now rearrange this and try to make it look like what we had before. So we get 1 minus x squared third derivative. And what do we have with the second derivative? We have, let's see, plus p prime prime. And then we have minus 2x minus 2x factor of m plus 1. And then we have just the p prime, which is going to be plus p prime l plus 1 minus m plus 1 minus 2m minus 2, which comes from this part. So let's begin by simplifying this part right here. So we can, well, let's begin by multiplying through this parenthesis. So we get minus 2xn minus 2x. Here we can clearly just factor out minus 2x. So we get, here we have 2 because we have minus 4x, and when we take this out we get 2 plus m. So let's just go ahead and write it in here. So instead of this we have minus 2x factor of m plus 2 p prime prime. And what happens with this? Well, l plus 1 is going to be the same, but here we have minus m squared minus m, and then we have minus 2m minus 2. Now we can factor this out actually. Well, there's several ways to do it, but you're going to see this is just minus m plus 2 m plus 1. Right? When we factor this, we're going to get a minus 2, then we have minus 2m minus m, which gets us minus 3m, and then minus m squared. So yes, this is just, and it might take a while to factor that if you haven't done that in a while, but you're going to see it's just this basic factorization process, which might be a little bit tedious, but worst case scenario you have to try a few things, but that's just what it is. So what happened here? When we took the derivative, we went from the equation above to this other equation, and let's take a look at it. They have the exact same form, except that for every m up here, here it is m plus 1. So here we have m plus 1, here we have m plus 2. Here we had m, now we have m plus 1. Where we had m plus 1, now we have m plus 2. What does this mean? And also, for every p, here we have an extra derivative. So instead of second derivative, we have third. Instead of first, we have second. Instead of none, we have 1. What does that mean? That means that if p is the solution for m, for some m, in this case we know it's the solution for m equals 0, then p prime is the solution for m equals that other m plus 1, but since we know it's 0, we know that p prime is going to be the derivative, at least p prime is going to be then the solution for m equals 1. And by the same procedure, you can actually go ahead and take the derivative again if you want, and you will see that p prime prime is going to be the solution when m is equal to 2. And actually, you can also see that it's going to be the solution as well if this is minus 1 or minus 2. And you can go ahead and show that by induction if you want, but you can actually just see in this procedure that that's the way that it is working. So what does that mean? That means that our theta that we had before, remember, this was 1 minus x squared times the solution of this equation, because remember, this was what we already had. This is to the m half power. So we have 1 minus x squared, and remember, since m can also take the negative values, we're going to want to take the absolute value of this. And now we know that the solution to this is going to be the nth Legendre polynomial of x, right? But there is just a small thing that we have to consider, but it's what we just discussed. We have to take the nth derivative, obviously absolute value, because it doesn't make sense to take the minus first derivative, because this is a solution either if m is equal to 1 or minus 1, it's the same. So we take the nth derivative with respect to m. And this is going to be our solution, and this is actually what is called the associated Legendre polynomial, which is written like this. So, and obviously in the end, we are now going to want to, instead of x, write all of this as with our original cosine, because x was cosine. So let's just write it as well, actually let's just leave it like that, because actually I think that's the way that it's usually written, and it might be more comfortable to work with. But remember, originally we had it at x, but it's just a matter of plugging it back in, the d by dx, putting it back. But this is the solution. But yeah, this is the Legendre polynomial. So remember, this is associated Legendre polynomial, which is the solution to the associated Legendre equation. And this part right here came back because, remember, previously, let me see, yeah, we said, okay, we want to solve this part, and then we have to multiply it by what we still have here, which, although could be solved mathematically, it doesn't really have much of a physical meaning. Now let me see if I can find, this was the solution, sorry, there it is. Wait, I'm lost again. I just found it. There it is, sorry. Okay, so now this is the solution to the to this angular, to the theta equation. So now let's just put everything together. So what exactly do we get for the angular? Because remember, the angular equation was this big theta times big phi. What are these things? Well, big theta, sorry, we know it's this associated Legendre polynomial, and this big phi is e to the I m. I'm using this notation for phi. There we go. So this is actually going to be the solution to the angular equation, which is the product of these two solutions that we found, and this is what is called the spherical harmonic. There is still something that has to be considered, though. This has some constant of normalization, right? That's important. And we want to determine that constant of normalization so we can actually find the definitive form of these spherical harmonics. So what is it going to be? It's going to be, well, how do we normalize this? What we want to have here is that this y prime, and y depends on L and M, right? We want y of some L and some M when you take the inner product of some other one with, let's say, K and N, right? Some different numbers. So if this is 2, for example, this could be 2 as well, or 1 or 3 or whatever. We want, when we integrate this over all of space, which means between 0 and p for theta and 0 and 2 pi, sorry, for phi, then we want this is going to be then sine theta d, whoops, I'm using this notation, phi d theta. We want this to be delta and m delta lk. Basically, we want it to be 1 if m is the same as n and if l is the same as k, and we want it to be 0 otherwise. But we want it to be orthonormal. If they are in the same state, we want this to be 1, and if they are not, we want it to be 0. And remember, now we have to multiply this by this a squared constant, which is our constant of normalization. So this is now the final thing that we have to solve in this problem, which is to normalize the spherical harmonics. And well, how are we going to do this? Well, let's write the form of these spherical harmonics. So this is going to be a squared 0 to pi. I think that before I had written the a inside of the spherical harmonics, but it's fine, it's the same. So just make sure not to write it twice. So in this first case, it's going to be PLM. This is real, so taking its conjugate will not do anything. So the first associated Legendre of LM, and also associated Legendre polynomial of Kn. And then we have e to the I m phi. Well, one is going to be negative, and this one is going to be I n phi. and this is going to be sine theta d phi d theta. Okay, so this is what we are now dealing with. Let's take a look at this. Well, we can see that we can separate these integrals, first of all, because of the fact that, well, everything is independent of theta and phi. There's nothing that is mixing those two quantities, because this right here only depends on theta, this right here only depends on phi. So the theta equation will be PLM PKN sine theta d theta integral from 0 to 2 pi e to the minus I m phi e to the I n phi d phi. Okay, so let's do this just step by step. Let's begin with this equation right here. Now let's see. First of all, what happens if n and m are the same? Well, in that case, this will just cancel out and we will get, well, it will be 0 to 2 pi d phi, because this right here will just be 1 and this integral is just 2 pi. So if m is equal to n, we get 2 pi. Okay, so let's just keep that in mind. I'm gonna write it to the side. I kind of wrote it bigger than I wanted to, but oops, well, it's fine. So I'm just gonna get rid of it. Let's just remember that result. Okay, now, oh, I took the 0 with me. Now what happens if m and n are not the same? Well, let's take this integral. So this is 0 to 2 pi of e to the minus I phi m plus, let's take the minus sign and leave it in here actually. So we get m, actually the other way, n minus m d phi. So when we do that, now we take the integral, we get e to the I phi n minus m divided by I n minus m, and we have to now evaluate this between 0 and 2 pi. What do we get here? Well, let's take this and factor it out. So we get 1 over I n minus m. So we get e to the I n minus m times 2 pi minus 1. Now, if you can't see what this is going to be, once again, use Euler's formula here. 1 divided by I n minus m. So we write this exponential as cosine of n minus m times 2 pi. Then we get plus I sine of 2 pi n minus m, and all of this just minus 1. And what do we have here? Well, n and m are both integers. So n minus m will either be, depending on the value, well, 0 or 1 or 2 or 3 or minus 1 or minus 2. It's going to be some integer. So we will always have some integer times 2 pi. So this will be always 1. This will be always 0. That means we will always have 1 minus 1. So this will always be 0. Now let's put these results together, because if m is different than n, this will always be 0. If they are the same, this will always be just 2 pi. So this will just be 2 pi delta n m. All right, so that is the solution for this first part, which is just the part of the phi. Now what we want to do is going to be to solve the second part of this integral, which is right here. Yes, is it? No, I think I went one too far. There we go, here it is. So now we want to solve, just put all of this together. So we have a squared sine d theta, and this is now going to be multiplied by 2 pi delta, it was n m. So actually now n and m have to be the same. So let's just write it as m, because otherwise this whole thing will just be 0. And okay, we have this 2 pi here. So what is this going to be equal to? Now here we have to use a property that I'm afraid I can't really just explain much, because It was quite long, and this is the orthogonality relation for the Legendre polynomials. So the expression for this is that whenever you take the inner product from 0 to pi of some PLM of cosine, which is what we are doing, PKM of cosine theta, sine theta d theta, this is going to be 2L plus m factorial, 2L plus 1L minus m factorial delta KL. This is the orthogonality relation for the Legendre polynomials. Proving it is very long. I looked into it to see if maybe it was worth proving it, but it is so tedious and it's really not in the scope of the course. So I decided that for once I'm just going to give us this and we will have to work with it. So let's plug it in here. So we get that a squared PLM PKM. Well, actually we already replaced this, sorry. So let's just go ahead and write it. So we get a squared 2 pi times 2L plus m factorial divided by 2L plus 1L minus m factorial delta KL. But the delta KL is something that we have already used here because K is already equal to L, and this has to be equal basically to 1 because we have already applied all the deltas. L is already equal to K, M is already equal to N, so we don't really need to write them anymore. And from this we can see that the normalization constant is going to be the square root of, and let's now take the inverse of this, so that's going to be 2L plus 1 L minus m factorial divided by 4 pi L plus m factorial. Okay, so finally with this we can now write the final form of our spherical harmonics, which are just going to be, it's going to be what we just determined, this constant of normalization times our associated Legendre polynomials, but evaluated at cosine theta, and this is going to be multiplied by EIM5. So this is finally the solution to this angular equation, and in the next video we will now go and solve the radial equation, which is where we will finally actually start working with the hydrogen atom, because as I discussed previously, this is actually a solution that is valid basically for every potential that is going to have this spherical symmetry. So I will see you then.